everyone, this is Juan speaking, and I'm the developer of FuzzyLite, a fuzzy logic control library in C++. Technology has been great for the past 20 years, to the point that I can safely assume that you have a mobile phone, you probably prepare rice in a rice cooker, surely you have prepared to take a lift over taking the stairs, and hopefully you have vacuumed your place at least once this year. Moreover, you have surely played video games in your lifetime. Perhaps you have done your own laundry. You know what a digital camera is, even if it is bundled in your phone. And probably you like to take long, perfectly hot showers as much as I do. Perhaps you have heard of Google's efforts towards a self-driving car. And definitely you have watched tons of movies, and being in New Zealand, it is compulsory to have watched Lord of the Rings. Also, you should know that most of them, if not all of them, use fuzzy logic control in one way or another. There are over 50,000 patents involving fuzzy logic control. Over $10 billion in product sales using fuzzy logic control, and I'm only talking about a single product, which is a blood pressure monitor. Now, the profits of the industry using fuzzy logic control are estimated in the billions of dollars. And the whole idea of fuzzy logic control started like 50 years ago or so. And can you possibly believe that state-of-the-art fuzzy logic control libraries have strong limitations even nowadays? Take for example MATLAB and its fuzzy logic toolbox. The last time I checked, you had to pay several thousands of dollars for both of them, as they are sold separately. And on top of that, you have to put up with one of the most horrible programming languages that have been ever made. Octave and its fuzzy logic toolkit, unfortunately they're doing the best they can to mimic MATLAB, but they're doing so with an open source GPL license, which might prove restrictive for closed source commercial applications. The people from JFuzzyLogic have made some unfortunate design choices along the way, and as for the other libraries, I have not seen one that is worth taking a look at. Therefore you can see why I started FuzzyLite in the first place. To be a free and open source project with a commercial friendly license, I like to think that I have made mostly fortunate design choices. It has more features than all the libraries available up to date combined. It is very easy to use, and it is available for the major platforms. The overall goal of this tutorial is to present an introduction to fuzzy logic controllers. Specifically, I will go over the design and operation of fuzzy logic controllers, I will present some examples, and lastly, I will describe FuzzyLite. So what's a fuzzy logic controller? Basically, it consists of a set of inputs that activate a set of rules that trigger a set of actions that generate a set of outputs. As simple as that. A classical example in fuzzy logic control is that of how much tip would you leave at a restaurant based on the quality of the service provided. To model this, we have a fuzzy logic controller that takes as an input the quality of the service. It generates the tip, exactly how much tip you're going to leave, based on a set of rules that are just common sense. I mean, if the service is poor, then the tip is going to be cheap, and if the service is great, then the tip is going to be generous. Having said that, the quality of service is a linguistic variable whose range goes between 0 and 10, and it is divided in 3 overlapping terms, namely poor, good, and great. Thus, if you rank the quality of service as 2.5, the term associated to that is poor. The tip is another linguistic variable whose range goes between 0 and 25, be it percentage or any other unit of your choice, and it is divided in 3 overlapping terms, namely cheap, average, and generous. And more interestingly, if the tip value is 17.5, the terms associated to that is average and generous, but it is not cheap. Now these are linguistic variables with crisp sets because For every possible value, the terms are associated with a degree either 1 or 0. That is, either the term is associated or it is not. For example, we have seen that for a service of 2.5, the term associated is poor, but it is not good nor great. And for a tip value of 17.5, it is average and generous, but it is not cheap. Now, if we add another dimension and we call it membership function, then we can better define the linguistic variables with different degrees of certainty that goes between 0 and 1. Thus, for example, for an x value of 2.5, we now say that the associated term is poor with certainty 1.0. Likewise, we define the membership functions for tip, and to make it more interesting, consider a value of y equals to 17.5, which should be around this place. Then we say that the associated terms is 0.2 average, which would be around here, and 0.8 generous, which would be somewhere around here. These are linguistic variables with fuzzy sets which allow to represent much more information using membership functions whose values are between 0 and 1. The design of a fuzzy logic controller consists then on modeling the inputs and outputs as linguistic variables and writing a set of rules that will provide the desired behavior. As such, the operation of this fuzzy logic controller will be as follows. So for a poor service, the tip is going to be cheap, but as the service improves, we see that the tip also gets more generous. It is important to understand the underlying operation of fuzzy logic controllers because it is at the very core of Fuzzlight. So, the moment that you rank the quality of the service, the fuzzy logic controller will undergo 3 stages, named fuzzification, inference, defuzzification, and finally we will obtain the output, which would be the tip. The first stage is fuzzification, and it basically converts the crisp values into a fuzzy set. You should know already how to do this. So for example, we have the input variable service, and fuzzification is basically defining the fuzzy set. So for a value of 1.0, for a ranking of 1.0, we say that the associated term is poor with a degree of 0.4. For a value of 2.5, we say it is 1.0 poor. For 7.0, somewhere around here, it is 0.2 good and 0.8 great. So we define the fuzzy sets as the sum of the membership functions for value x over the label of the term. The next step is inference, which activates the rules to generate fuzzy outputs. So having the fuzzy inputs from the previous stage, we work first on activating the antecedents, then we modify the consequence of each rule, and finally we accumulate the whole thing together to obtain our fuzzy outputs. The first step is the activation of the antecedents, and considering the example that we have worked so far, taking an input value of 2.5 for the service, we assign the values from the membership functions to each of their corresponding propositions, and ultimately we will have an activation degree for each antecedent. Now, considering the more interesting case of an input value of 7.0 for the quality of service, we assign 0.0 to the proposition service is poor, 0.2 to the proposition service is good, and 0.8 to the proposition service is great. The next step is the modification of the consequence. So using the activation degrees we have computed before, we multiply them with the linguistic linguistic terms in each of the consequence using an activation operator, which is some sort of fuzzy multiplication, if you will, but it is formally known as a t-norm. For example, if we multiply 1.0 with the linguistic term cheap, we get the linguistic term exactly as it is. Whereas as we multiply 0.0 times average, we get nothing, and 0.0 times generous, we get nothing either. Now, if we make it more interesting, say the multiplication of 0.0 cheap, 0.2 times average, and 0.8 times generous, we will get the following, provided that we define the fuzzy multiplication, or the activation operator in this case, as the minimum between any two possible values. So we say 0.0 times cheap, the minimum will be 0 all throughout. Now 0.2 times average will be the minimum as soon as we reach 0.2, where it becomes the new minimum. It goes all the way until it goes down. And lastly, 0.8 times generous, using the minimum as an activation operator, we will get every possible value until we reach 0.8, and then we get the rest of the values. Now, if we define the fuzzy multiplication, or the activation operator in this case, as a proper multiplication as we know it, then what we're doing is basically we're scaling the membership functions to the activation degrees. So 0.0 cheap would be still 0. 0.2 average, you see that we have scaled a linguistic term to 0.2, and likewise we have scaled the linguistic term generous to 0.8. The last step is the accumulation of the consequence. So we're going to sum up everything, and considering the more interesting case for a quality of service ranked as 7.0, then the first step we have performed is the activation of the antecedents, which we already got. Then we use those activation degrees to multiply them with the linguistic terms of the consequence. And now what we want to do is we want to accumulate all together. And we're going to do this by using some sort of fuzzy sum, if you will. In this case, we name it accumulation operator, which is formally known as an S norm, or some other people may argue that is called a TICO norm. Now recall the examples that we went through before, the modification of the consequence. What we want to do is to sum each of these terms. So let's start with the left one first. And we're going to define the fuzzy sum, or the accumulation operator, as the maximum between any two values. So look at the shape we have, and it's sort of choosing the maximum between any two possible values of this term. So the maximum will be this one, and the maximum will be this one, until we get the rest of it. Now, if the other case that we can also do is define the accumulation operator as a proper sum, as we know it, 1 plus 1 equals 2. So in this case, we will have the sum between this one is 0, 0 plus this one will give me this one, and then here we sum this value with this value, which will give us some sort of continuation here, as it does. This is the end of the inference stage, and now the question is, what do we do with these shapes, which are actually fuzzy numbers? How do we make sense out of them? And the answer to that lies in the diffusification stage. The diffusification stage converts fuzzy outputs into crisp values, and a typical example is a centroid, which integrates over the fuzzy number, computes the centroid, and returns the x coordinate of the centroid. Other examples are the maxima diffusifier, which can return the smallest, the mean, or the largest uh, x value from the maximum membership function. And after the diffusification, we have the output values of our fuzzy logic controller. So let's take a look at some examples. This is Qt Fuzzy Light, and the example that I'm going to show you is the simple dimmer. So the simple dimmer is a fuzzy logic controller to automatically dim the power of a light bulb based on the amount of ambient light that there is. So if the ambient is dark, we want the power of the light bulb to be high. If it is medium, then the power is medium. And if the ambient is bright enough, then we want the power to be rather low. So we model the input variables using simple triangles, and they go between 0 and 1. And you can think of this as the values that you obtain from a light sensor. Now the power of the bulb, of the light bulb, is modeled again using triangles, and it goes between 0 and 1. Now if we go to the control tab, then we can actually play with the fuzzy logic controller. So as I move the slider, you can see the different rules activating to different degrees as the ambient becomes brighter. Now these activation degrees are shown as the strength and also in colors with different shades of green. And on the side of the power of the output variable, you can see this green shape is the accumulation of the outputs that we have defined before, and this line is the result of the diffusifier, which is given by the centroid, and it follows the small circle that indicates the centroid of the shape. So you can see how it all works together. Now another way of viewing this is as an output view. So we can actually see the changes in time based on the input values. The other example I wanted to show you is the investment portfolio from Octave. Now in this case there are two input variables, namely age, which is defined by two linguistic terms, young and old, and it ranges between 20 and 100 years old, and risk, defined by two linguistic terms, low and high, between 0 and 10. Now the output variable is the percentage in stocks, and it's defined with three linguistic terms, and it goes between 0 and 100. Now I'm not sure much of what this fuzzy logic controller does, but based on the rules you can get an idea. So if you're young and you present a high risk, then the percentage in stocks is about 85. Now otherwise, if you're old and your risk is rather low, then the percentage of stocks is about 15. Now this reminds me, these rules reminds me that another use of fuzzy logic controllers is in the in banking and insurance companies. So a bank would decide how much money would they loan you based on different variables, and an insurance company would decide how much the cost of your insurance policy would be based on other variables and rules expressed like this. Now the reason why I like this fuzzy logic controller is because it introduces the concept of hedges, say not extremely, and you have some others that will help you build more flexible controllers. The other aspect is this with 0.5. 0.5 determines the weight of the rule, the importance of the rule. So in this case, these two rules will have the importance as the previous two. Another important thing to mention here is the use of the T norm, S norm, and the activation operator, which we have defined before. The activation operator, you already know it. But T-norm and S-norm in these cases, the T-norm is for the it defines the operation of the connective and the S-norm defines that of the connective OR. In Fuzzy Light, you are currently enforced to, as of version 3.1, you are enforced to select either, to select both of them, the T-norm and S-norm, even if you do not have a connective in your rules. However, that will change in version 4. Now, going to the control tab, you can play with the fuzzy logic controller again and see how it operates and how the different rules activate and the accumulation of the outputs happen. But another way of seeing this is using the surface 2D, which will create a map of the output values of the percentage in stocks based on the inputs, or on the different possible values for the input variables. So in this case we generate the map, and you can see that as the age is older and this one would be the risk, as the risk is smaller, you get a more yellowish output value, a smaller value in other words, and red otherwise. You can also remove the contours or add more contours as you please, and you can of course save that image as you want. Now lastly, I wanted to tell you that you can create your fuzzy logic controllers from scratch using the user interface using Qt Fuzzlight, and you can also export them to C++, to the code in C++ easily, so that shouldn't be a problem. Moreover, you can export it to fuzzy logic, to the fuzzy control language or the fuzzy inference system of MATLAB, and you will get everything there. So, going back to our presentation, Fuzzlight is a library. You can build it as a dynamic library using, in Linux would be .so, and Mac .dylib, or in Windows .dll. You can also build it as a static library if you want. And Qt Fuzzlight is just a user interface that links to Fuzzlight. The main features of Fuzzlight are Mandani, Takagi Sugeno and Tsukamoto fuzzy logic controllers. The Mamdani controllers are the one that I have explained in this tutorial, and the others are, you can read the paper which are explained there. Fuzzlight has over 17 linguistic terms, 13 fuzzy logic operators to model your fuzzy sums and multiplications, that is your T-norms and your S-norms, 7 diffusifiers, 6 types of hedges that I have told you before, including vary, somewhat, and not. You can import and export using different formats, also export to Fuzzlight C++, and you can easily extend and incorporate new components to Fuzzlight. This is the list of linguistic terms that are available in Fuzzlight, but there are also some others that allow you to combine different linguistic terms if you need it. And lastly, this is the abstract model of Fuzzlight. So we have an engine that is the controller itself. So you have a vector of input variables, a vector of output variables, a vector of rule blocks, and a vector of hedges. Every time you set the values for input variables, you call process, and then that should be it. The input variables have an input value that is a type scalar that can be defined as a float or as a double, and a list of terms, and a vector of terms. Now the rule block contains the rules for the fuzzy logic controller. The T-norm and S-norm are going to change in version 4, The T norm defines the conjunction, that is the AND connective, and the S norm defines the OR connective. This is the activation operator, and fire rules triggers all the inference process together with all the inference process. Lastly, the output variable also has a vector of terms, an accumulated output, which we have defined before, a diffusifier, and a wrapper called diffusify, which makes the diffusifier diffusify the output, the accumulated output. Now, as conclusions and future work, well, we have shown that fuzzy logic controllers are a very powerful alternative to traditional control algorithms. They are very easy to design and operate, and also to maintain over time. And there are several algorithms to tune fuzzy logic controllers to improve their performance. However, it is important, very important, to recognize when it is useful to utilize fuzzy logic controllers. Because if you take a look at the example that we have shown so far, you can easily model this behavior using a simple function from the ramp term. Now, this function will be far more computationally cheaper than using a fuzzy logic controller. As for future work, I expect to incorporate type 2 fuzzy logic controllers, which include uncertainty on the membership functions, develop the adaptive neurofuzzy inference system, which includes neural networks and fuzzy systems, and the fuzzy C-means clustering algorithms. But there are still many more things to do. Well, I hope that you have enjoyed this tutorial, and if you have enough resources, please consider supporting Fuzzylite with a donation. All the money goes strictly to the development of Fuzzylite, and I am currently working on a Java version which I expect to release early 2014, but your donation would make an important difference. Thank you very much.